Welcome back to G Fun Facts Online. Today, we are turning our gaze upwards, but not to the distant galaxies or nebulae we usually discuss. We are looking at the space immediately surrounding our planet, a region that is undergoing the most radical transformation in human history. For millennia, the night sky has been a static canvas. It was a source of navigation for sailors, a storyboard for mythology, and a source of wonder for anyone who looked up. But today, if you go to a dark sky site and look up at just the right time, you might see something that doesn't belong. You might see a train of bright lights marching in a perfect, unnatural line across the stars. This isn't an alien invasion. It is a newly launched batch of Starlink satellites climbing to their operational orbit. This visual phenomenon is the face of a profound technological shift. We have entered the era of the mega-constellation. While these networks promise to bridge the digital divide and bring high-speed internet to the most remote corners of Earth, they are also fundamentally altering the environment just above our atmosphere. This new reality has given birth to a critical new field of study called orbital ecology. Just as we study the delicate balance of ecosystems on Earth, like the rainforests or the oceans, we must now understand the complex, finite, and fragile environment of low Earth orbit. To understand why this is happening now and what the risks are, we first need to look at the new architects of orbit. The landscape of space is being reshaped by a few key players, each with a different philosophy and a different impact on the orbital environment. The undisputed titan of this new era is SpaceX with their Starlink constellation. Starlink is operating at an altitude of roughly 550 kilometers. This is a very specific choice. By flying this low, they ensure low latency, which is the time it takes for a signal to travel up to the satellite and back down to you. This is crucial for things like video calls and online gaming. However, the physics of low orbit dictates that a single satellite can only see a small patch of the ground at any one time. To maintain continuous coverage, Starlink relies on a strategy of overwhelming force. They need thousands of satellites to blanket the globe. Their network is designed with shells at different inclinations, essentially wrapping the Earth in a mesh of data. But they are not alone. Another major contender is OneWeb, backed by European interests. OneWeb takes a fundamentally different approach. They operate much higher, at around 200 kilometers. This higher vantage point allows them to see more of the Earth with a single satellite, meaning they can cover the globe with hundreds of satellites rather than thousands. It also makes it easier for them to reach the polar regions. However, from an ecological perspective, this altitude comes with a distinct risk. At 550 kilometers, where Starlink lives, there is still a tiny bit of atmospheric drag. If a Starlink satellite dies, gravity and friction will naturally pull it down to burn up in the atmosphere within a few years. But at 200 kilometers, where OneWeb lives, the air is too thin to do that. Satellites at that altitude can stay in orbit for centuries. This means a failed satellite at 200 kilometers becomes a semi-permanent piece of space junk unless we actively go up and remove it. Then there is the sleeping giant, Project Kuiper, backed by Amazon. Although they are late to the party, they have massive capital behind them. Kuiper plans to launch over 200 satellites into shells similar to Starlink's, occupying the altitudes between 590 and 630 kilometers. When Kuiper comes online, it will effectively double the density of traffic in these prime orbital highways, testing the limits of our current coordination systems. This brings us to the core concept of orbital ecology. We need to stop thinking of near-Earth space as an infinite void. It is not infinite. It is a finite natural resource, a habitat that can be polluted, congested, and ultimately ruined. The nightmare scenario for orbital ecologists is known as the Kessler syndrome. This was proposed by NASA scientist Donald Kessler way back in 1978, and it describes a cascading chain reaction of collisions. To understand this, imagine a busy highway where a single crash happens. That crash creates shrapnel. That shrapnel flies across the road and causes 3 more crashes. Those crashes create enough debris to cause 10 more. Before you know it, the entire highway is unusable. Now apply that logic to space, but with much higher energy. In orbit, debris moves at roughly 17,500 miles per hour. At these speeds, kinetic energy is enormous. A fleck of paint hitting a satellite hits with the force of a bullet. A small screw hits like a hand grenade. We have already seen precursors to this terrifying chain reaction. In 2009, a defunct Russian satellite known as Cosmos 2251 slammed into an active Iridium communications satellite. It wasn't just a bump. The impact created a cloud of over 2,000 pieces of trackable debris, and likely tens of thousands of pieces too small to track. That debris cloud is still up there, crossing through orbital lanes, posing a threat to everyone else. In the era of mega-constellations, the target density is exponentially higher. A runaway event could render specific orbital altitudes unusable for generations, effectively trapping us on Earth behind a barrier of high-velocity junk. To prevent this orbital clutter, companies like SpaceX follow a philosophy called design for demise. The idea is simple. Build satellites that are designed to burn up completely in the Earth's atmosphere at the end of their 5-year lifespans. This sounds like a perfect solution for the debris problem. If the satellite burns up, the space stays clean. However, matter cannot be destroyed, it only changes state. When a satellite burns up, it doesn't vanish. The aluminum chassis vaporizes and turns into alumina, or aluminum oxide particles. Recent studies suggest that depositing tons of alumina into the upper atmosphere could trigger unforeseen chemical reactions. We are effectively conducting a massive, uncontrolled chemistry experiment in the mesosphere. These particles may reflect sunlight, accidentally geoengineering the climate, or they could catalyze ozone depletion, undoing decades of recovery in the ozone layer. Furthermore, the rockets used to launch these thousands of satellites emit black carbon, or soot, directly into the stratosphere. Unlike ground-based pollution which washes out with rain, stratospheric soot lingers for years. It absorbs heat and has the potential to alter global jet streams. So, while we are solving the digital divide, we might be creating an atmospheric crisis. The impact is not just environmental, it is also scientific. We need to talk about the astronomers' plight. For astronomers, the impact of these mega-constellations is immediate and optical. In long-exposure photography, which is essential for seeing faint objects in the deep universe, satellites appear as bright streaks. These streaks can completely ruin the data. This is a major problem for upcoming projects like the Vera C. Rubin Observatory. This is a wide-field telescope designed to survey the entire sky every few nights. It is expected that the Rubin Observatory will see thousands of these satellite streaks every single night. This interference could blind us to transient cosmic events, like near-Earth asteroids headed our way, or distant supernovae that tell us about the age of the universe. And it is not just visible light. Radio astronomers are facing a blinding noise floor. Satellites beam high-speed internet data down to Earth using radio frequencies. These beams can bleed into the protected bands used by radio astronomers to listen to the whisper-quiet signals of the early universe. The aggregate interference creates a radio smog that no remote mountain location can escape. There have been technological mitigations attempted. SpaceX initially tried painting their satellites black, a project called DarkSat. However, this caused thermal issues because the black paint absorbed too much heat from the sun. They then tried deployable sunshades, known as VisorSat, to block the reflection. The current standard involves using advanced dielectric mirror films on the bottom of the chassis. These films scatter sunlight away from the Earth, making the satellite appear dimmer to observers on the ground. While this is an improvement, it remains a cat-and-mouse game between engineering and the extreme sensitivity of astronomical instruments. All of this brings us to the question of governance. Who is in charge of space? The reality is that technology moves at the speed of light, while regulation moves at the speed of bureaucracy. The primary body governing orbit is the International Telecommunication Union, or ITU, which is a United Nations agency. Historically, the ITU assigns orbital slots and radio spectrum on a first-come, first-served basis. This archaic system has led to a land grab. Companies file for tens of thousands of what are called paper satellites. They lock in the rights to these orbital slots even if they never intend to launch them, just to block competitors or sell the rights later. To manage interference, the ITU uses something called equivalent power flux density limits, or EPFD. These are complex mathematical equations ensuring that a moving satellite doesn't shout too loudly over a fixed geostationary satellite. However, these rules were written decades before mega-constellations existed. They struggle to account for the aggregate noise of 50,000 satellites all shouting at once. There is some progress, however. In a positive move, the U.S. Federal Communications Commission, the FCC, recently tightened its rules on space debris. They now require satellites to deorbit within 5 years of the end of their mission. This is a significant reduction from the previous guideline, which allowed dead satellites to linger for 25 years. This new rule is a major win for orbital ecology, enforcing a carry-in, carry-out policy for campers in space. Looking to the future, the only sustainable path forward is a circular space economy. We need to shift from a launch and burn model to one of repair, reuse, and removal. We are finally seeing the birth of interstellar janitors. This is the field of active debris removal. For example, the European Space Agency has planned the Clear Space One mission for the 2025 to 2026 timeframe. The goal is to capture a Vespa payload adapter left in orbit by an old Vega rocket. The mission will use a robotic spacecraft with a 4-armed claw to grab the debris and drag it into the atmosphere to burn up. Another company, Astroscale, launched a mission called ELSA-D, which successfully demonstrated magnetic capture technology in 2021. The idea is that future satellites could be launched with magnetic docking plates, effectively tow hitches, making it easy for a service removal satellite to grab them and take them out of orbit when they fail. The technology for cleaning up space exists. The hurdle, as is often the case, is economic. Who pays to pick up the trash? Currently, it is mostly government space agencies funding these demonstration missions. But the insurance market is watching closely. In the future, we may see orbital tolls or mandated disposal insurance premiums. This would mean that the cost of cleaning up a satellite is paid for up front, making orbital sustainability a line item on every launch manifest. We stand at a pivotal moment. The decisions we make in the next decade will determine whether low Earth orbit becomes a thriving engine of global connectivity and commerce, or a junkyard of high-velocity shrapnel. Orbital ecology is no longer a niche academic term. It is the governing principle of our future in space. To preserve the heavens for navigation, for science, and for wonder, we must learn to be better stewards of the void. Thank you for listening to G Fun Facts Online, and keep looking up.